Okay. So I think I prepared a talk on explainable AI. So, and I was naming it Understanding Machine Learning Models. And I will introduce you to the concept and to one of the workhorses in this field, and also give some applications. So many of us are using machine learning methods, and many of us have been complaining that these are black box models. And of course, people like to complain, but I think it should not be about this topic. So machine learning models are not black boxes anymore. And I will share with you a line of research that we've been pushing together with a community that has been forming. So let me just briefly give you an idea. Assume that you have trained some model. It could be a deep model. It could be a support vector machine. It could be an LSTM, whatever you want, right? And so this model is trained and fixed. So now you would like to understand, for example, here, this model would be AlexNet, which is by Alex. And it is trained to do predictions of, computer vision images well. Whether, this is some very sensible task, we can discuss about that. But, it can recognize roosters very well, and cats and dogs and buses and parties and whatnot, okay? So assume that you are now giving a new data point to this model, which is, for example, a new picture of a rooster that the model has never seen. Sure enough, since the model is generalizing well, it will classify this into the rooster class. So now you wonder, why does this model consider this particular image to be a rooster? And the problem with this is that the whole model that we are looking at is a highly nonlinear beast. So it can't just, if it were a linear model, it would be easy. But since it's a nonlinear model, it's not. And so from the mathematical point of view, you have to somehow put this nonlinearity, this nonlinear function, upside down, and then have to go backwards through the model somehow, and then give some probability map to each pixel of this input picture, which tells you which of these pixels are super important for the classification. So, and you can see by looking at the slide that it's really the rooster's comb, right, that this model considers important. So let me just explain a bit more. So assume you take a very simple problem, and this is like old data from Fisher, and it's the iris data. So irises are plants, flowers, and the idea in this iris data was that you would get, so the irises have these leaves that are called sepals, right? And so you can consider the length of the sepal and the width of the sepal as two features. And then, there's different irises, and you put them, into this, feature space. And so you can see that, the blue ones are the versicolor, and the red ones are the setosas, and the green ones are the virginicas. So you could, for example, build a linear model, and like that, which is a very lousy one, clearly, as you can see, right? And this linear model would be super easy to explain, because basically if you go from here to there, the explanation is basically this variable. So it's all about the sepal width. But you can clearly see that this doesn't cut it. But generally, linear models are super easy to explain. So if you have a nonlinear model, then things are getting more complicated. Because, for example, I'm now considering this nonlinear model. You know, some red setosas are classified because of their sepal width. Some are classified as setosas because width and length. And for example, this is a Virginica because of the length thing. Okay, so you can see that locally, if you have a nonlinear function, there's different information that makes you explain that. But it's worse than that, because you know, the local picture is not telling you everything. But if you think about the data as lying in some manifold, then you know there's also some global structure. So just looking locally is not enough. Okay? So it's hard. Second thing is, so in most of the time, or a standard exercise in machine learning has always been to do feature selection. So feature selection is a different point of view. So in feature selection, you're asking, in the ensemble of all the data that you have in your training, you would like to know which of the features of all the data are particularly telling for one class. So the point of view that I'm taking here is an individual explanation, an explanation of an individual data point. So that's a different question to ask. Okay? So assume that, for example, you classify this boat, and again with AlexNet, then you have this nice heat map which basically tells you it's essentially the wheelhouse, right? So that lights up. By the way, green is neutral, blue speaks against this. So here, a sailboat would, you know, be considered a boat mainly because of the sails. And here, this boat is not even in water, so that's the bow that is quite characteristic. So if you would go to the feature selection question, which is a different one, like you could say what are the important features for the whole ensemble of data, and that is, of course, you know, a funny answer that you get. I mean, basically, it says that if you take pictures of boats, they are usually in the middle of the image, right? So feature selection is different from what I'm talking about.
But Klaus, for the right picture, you have averaged all of these activations. So what is the...
Yeah, that's one way, but there's also another way that you play the L1 thing. Right. Okay. So, as you saw, at least from these nice heat maps, there's some hope, and we should say goodbye to the black box. There's no more black boxes. There's a lot of activity in this field, and I should crowd this a bit more, but there's some historical remarks. What is called sensitivity is an old concept that, you know, people in control have been using, you know, last century. So just taking the input, wiggling a bit, and seeing, you know, how things change. That's called sensitivity. But it has been rediscovered several times, also from us, also from Simonian. What the pictures that you saw are from layer-wise relevance propagation, which is, you know, giving something rather meaningful in terms of Rooster's comb and so on. And there's a lot of methods that are based on this, or that are special cases of that. And there's also deconvolution methods, methods that need some kind of optimization, and so on and so forth. So let me just more precisely ask this question. So in the case of explanation, we ask, which pixels contribute how much to the classification? So in the case of the rooster, it's clear it was the comb, right? So what makes this image to be classified as a rooster, car, whatever, right? So in the case of sensitivity, you're asking, if I take the gradient to the function, so f is the function that I'm looking at, the deep net, whatever, then we can, basically the sensitivity or saliency asks which pixels lead to a decrease or increase in the prediction score when changed. So this is clearly a different question. So the question is, what makes this image to be classified more or less a car, or more or less a rooster? It's a different thing. And deconvolution is another beast overall. Each of them solve a different problem, and I think the first step is to be aware of what problem you actually have. So I'll now explain a bit about layer-wise relevance propagation, just the idea. So we all know in a neural network we have a forward pass. So in other words, we get something in, then the data is transformed and rotated and sheared and whatnot, goes through nonlinearities. And if this is going through several layers, then, and several means a large number, then it's called the deep model. So deep learning is nothing that is, it has become popular, but it's not something that has been invented recently. So deep learning has been around since, last century. Fukushima, for example, was one of the persons that had like a first deep model in the 60s. So now, how do we get the explanation? So assume, so we keep this fixed, all the parameters, everything. So we make a forward pass, and then we get some result at the forward, at the classification level for the classes. And now we say whatever the output of the model is, we call this a relevance, okay? And now we try to decompose this and move backwards to the input. So in other words, we would like to go backwards, meaning, let's look at what is the relevance for this node here. And the relevance for this node is basically a superposition with the weights that the model has learned, normalized, multiplied with the activity from the forward pass. So this looks innocent and makes some sense, and it's an algorithm like many that are in the field. However, there's not much that people have been able to prove, right? So there's a lot of algorithmics, but proofs are rare. So this was the first one, which could explain that what we are doing here is not arbitrary, but it does something which we can explain with what we call a deep Taylor decomposition. And I will just do some hand waving to explain that. So assume that you have some function, then a canonical way would be to do a Taylor decomposition. Just, any Taylor decomposition would give you, some kind of approximation of this function. So the problem in the Taylor decomposition is that there's a global root point, and then there's many higher order terms. These need to be approximated, and that's a nightmare and cannot be done practically. So a Taylor decomposition, a simple Taylor decomposition, doesn't work. In the case of a deep Taylor decomposition, the idea is the following. So you do a local linear decomposition around different root points. So every of these nodes does something local linear around a well-chosen root point, and then you can prove that this is doing the same as a global Taylor. So that's nice. And that's basically what this formula is implementing. Because as you know from school, local linear means global nonlinear. Right? So there's some more ingredient that we need. If we think about the relevances here across the layers, then we would like them to be conserved, right? And given all that, we can now get pretty pictures, right? As you've seen many of these in my talk already. So assume that you have a neural net, again AlexNet, then you put in this, and it's classified as coffee, and the reason for that would be the crema here, right? Or, the fluffy part of the back of the cat's legs would be, very much telling for the cat. Now, if you instead train a support vector machine, then, it's a different explanations for different cats. It's always the fluffy part or the mustache or whatnot. Okay? So, but the point of this slide is not the cats, but the point is that there are lots of models and you can always transform them in a way that you can apply this, Patrick.
This may not be the right time for this question, but one of the things that's always bothered me about this is sometimes the information that's not there is really important. So your rooster example,
yes.
It was in fact a hen, and the fact that there was no crest on the head was the most important thing. You can't explain that pixel-wise, right? You can't, there's no sense in which you can say that.
Right, but I mean, this was actually a rooster in the...
A rooster, yeah.
Yes.
Right, no, I'm saying, but flip it around. If it
yes.
was a hen,
yes.
It's a hen because there's not one of those, right?
Yeah, that's a very, that's actually a very interesting point. I actually got I show you later. I got this morning my student, and in fact my postdoc, who is in fact Wojtek Samik's lab, Sebastian Lapushkin, he sent me a very nice picture about some elephant and a zebra. Okay, and so you can see, then you classify this, and of course, as you know from Monty Python, they're African and Indian elephants, right? And so if you now look at the heat map, then interestingly, because this is in Africa, if there's a zebra and an elephant, there's actually a strong, if this is considered an elephant from India, then it speaks a lot against the zebra. Whereas if it's an elephant from Africa, then it speaks less against the zebra, which is a very interesting finding. So in that sense, it's almost what you're saying. So I can show you the picture afterwards. But I come back to this as well. Okay, so let me just digest a bit. Here's an image with a lot of scooters. I show you the heat map of this generated by the sensitivity, which is the gradients. And you can see it's a mess, which comes from first gradient shattering effect, and because this is actually not asking the right question. So here you will find a lot of activity here. So there's actually no scooter on the road, but of course you can think of changing these pixels until they become a scooter. So because sensitivity asks what makes a pixel more or less of a scooter, right? So LRP would be having nice, shapes of tires and, backlights and whatnot. Okay. So next is we can say something positive and negative, right? So which we're approaching your question. So this is classified as a 3. It's classified as a 3 because there's nothing here, right? No pixels filled. So you can also ask, why would it be classified as a 9 And there's some positive evidence because the 9 also has something here. But there's nothing here, right? So this is why this is not a 9. So LRP can say something positive and negative about things. And now I would like to play a video because it shows very nicely about these positive and negative aspects. So this is again Sebastian Lapushkin, right? And so he's been making this video, as you can see, and he's in front of a camera, so this is real time, and so it's a gender classification thing. So red speaks for whatever this is classified for. So if it's classified as a man, in red we will see evidence why this is a man, and blue against it, right? And if it's classified as a woman, then it's the other way around. Okay. So you see, it's classified as a female, but somehow the nose, has some hair. So it speaks against it. So that's speaking for the female part, as according to the classifier. Now it's not sure anymore about male or female, certainty low. Okay, now it becomes male, female, male, and then it's male clearly, right? And you see why. And this is now female, and the beard speaks against it. Male, female. So you can see, some very nice view in the inner workings of this algorithm. It's actually a lot of fun, and you can imagine how public the public likes this. Everybody likes to play with it and fool it, right? Okay. So clearly, we would not like to spend our time looking at cat pictures and roosters and African and Indian elephants. Just eyeballing this and saying, oh, this is nice as an explanation. We need to be a bit more quantitative. And in 2017 we published a paper on this. It's a very simple first approach to having this a bit quantitative. And its question is, how do we find out whether this is a good explanation? And the idea is to take the pixels that are speaking mostly for something or against something, we can change them, right? And then we change them one by one, and then we see how the classification breaks down. Already in the video you could see how the classification switches, right? Depending on what features are looked at. So here's pixels that we exchange, okay? And bang, the classification drops, okay? So we can take this curve and draw another curve where we do a random pixel flipping. And then we take the area between these curves, and that's a good measure of how good an explanation is. Then we can apply this to all sorts of data set and happily see that the LRP is not so bad. But we can also do some more interesting things. So there are some data sets around where you have the image and which comes with a bounding box. So you can actually ask the question, is a certain method looking at the object or not? And so you can see that, for example, one classifier basically classifies boats because of the water, and the deep model doesn't do it because it looks at the boat itself. So you can see boat, right? So most of the activity is inside the bounding box, whereas in this other classifier, Fisher, it's outside, right? So you can analyze this, you can quantify it. And I think this is important because it's important to understand the strategies that these models use. Okay, so of course you've seen a classification to gender. We can do this also to age. The funny finding that we had in our classification to age was, some people of the class of elderly people were systematically classified to be younger. Okay? And so we wondered why this is the case. And so we looked at it, and we found that in these cases, the elder people are smiling. So the data sets that are around for age, gender classification, but mainly age classification, elderly people are never smiling. They're looking so serious. So, I mean, I think that synchronizes well with our, human judgment. I think if somebody is happily smiling, you would consider him a bit younger. So that's the take-home message. But the point is also, we can easily find biases in this. And a lot of data sets around, they suffer from biases. So we can apply this to documents and see which keywords speak for some concept, against some concept. We can apply this to LSTMs. So the LRP for LSTMs was done in 2017. And for example, there's some data sets where we have different features, namely text and images. So that's the visual question answering thing. So there is a metallic cube. Are there any large cyan metallic objects behind it? Okay, that's the question. And then the question is, what does the explanation do? The explanation tells us this is the object, and then behind is the important concept. So which is interesting because you can imagine, I mean, this is now text and images, but you could also think about all sorts of different modalities and apply this cross-modality. Okay, so I continue. And so we all know, because we've been taught, that machine learning models, they're learning from data, and we try to have them generalize well. So we have our ways to do that by cross-validation and by proper model selection. And so the question is whether the generalization error is telling us all we need to know. In principle, yes. But practically, except for the Google people, we have most of the time finite data. So it's a question of whether the generalization error is so telling if we base it on finite data, or if it's giving the full picture. And I'm talking practically. So here's one of the typical exercises being done in computer vision. So computer vision is a great field. It's tremendously successful, and it has, gained some of its success by providing benchmarks over time. These benchmarks allow to test models. And here's two models that we consider that you already seen before, Fisher and the deep net. And they are classifying stuff, and that's the test data. So assume that you have a really good model, then it's much better than anything existing on the benchmark. Then you're happy and write a CVPR paper. That's a bit of a shorter version. But so imagine you have all these different concepts, and you can see the deep net is clearly better in some cases it isn't. So for example here on horses, the deep model is as good as Fisher. So you just get the generalization error, and you don't know whether one model is better than the other, statistically, right? So both models are very good. So Now we have our machinery in order to analyze things, and we can look at the heat maps. So here's a new picture that gets in. And both of these models say that it's a picture of a horse, which makes some sense. And the deep model says it's a horse because, you know, the horse has a butt and the nose and there's a rider. Okay? So that's okay. It's an object. This model also says it's a horse, but it's partly because of the butt, but partly, you know, partly because of this, right? And then we can look at what is there. There's certainly no horse. And this is a benchmark data, right? This is, you know, a benchmark from computer vision that has been there for a decade. Everybody is basing his stuff there. Now we have new benchmarks in computer vision. So I read this to you. There's a copyright tag that says Lothar Lenz Pferdefotoarchiv.de. So, you know, it's a copyright tag. This model classifies horses because of the copyright tag. It does it well. So you can see that there are different strategies in these models, and some of them are, you know, I would say appropriate because we are thinking about the concept and the object, and some of them are more towards the cheating part, right? It's quite intelligent behavior, by the way.
That's my question. Why is it cheating? This information they use?
Yes. So exactly. My wife said the same thing. So she said, "Why are you worried about this result? The model can read." Yes. Let me just continue, and then we come back to this. Okay, so here's another horse, a famous horse from history. I don't know whether any of you have seen it. This horse has the name Hans. It's a horse from Berlin. Since many of the participants this time are from Berlin, you know, they can relate to this very much. This is a picture from 1900, and the fantastic thing about this horse is that allegedly it could do math. And that was a sensation, right? And it was it was called Clever Hans because of that sensation. So basically, the horse would get a math example, and it should say what the result is. Of course, horses can't speak, but they can tap. So the master would point to some results, and the horse would tap if it's the right one. And the horse would predict always correctly. And that was really fascinating to people. And they wondered why horses can do math. And practically, the horse could very much read the master. So the master was more excited about something. Didn't show it explicitly. You couldn't see it if you were not a horse. And if you would exchange the master with somebody else, it would still work. The horse could feel it, right? So the horse was giving the right prediction for, you know, the wrong reason in some sense, right? So it couldn't do math, but it could solve the problem. So it's called the Clever Hans strategy. So clearly, this one is using a Clever Hans strategy. So a lot of models out there, they may be using Clever Hans strategies. In fact, we had a paper that discussed this particularly. And I still get some emails saying, yeah, we also found some Clever Hans strategy, but okay. So you can tell anecdotes like that all the time. So practically, it is important to unmask these Clever Hans strategies. If we're using neural networks in the sciences, or in medicine, it is super important that we know what kind of strategy these models are using. Now, people criticized our work with the horse and said, well, you know, that's nice. You have these heat maps, and of course you can look at these heat maps, but you know, what's the point in looking at the heat maps? We could also look at the pictures. You know, so what do we gain? So this doesn't scale, right? That's one thing. And also they said, you know, the model that you're using, AlexNet, is not state of the art, and you know, Fisher, who uses Fisher, and you know, complaints like that. And so therefore we thought, I think it's really not the issue of AlexNet, and it's really, we have to bring this to scale. And there's a very simple strategy that we suggested that was also published in this paper here. So the idea would be, again, you have your model, and you put in your data, you classify it. So then you can, of course, on the test data, get lots of heat maps. It's blazing fast. It's a linear algorithm. Scales. So then you have all these classification results, plus all these heat maps. Now you can cluster them. You have to normalize them appropriately, and then apply spectral clustering. So in spectral clustering, basically the algorithm tells you from the eigenvalue from the eigenvalue spectrum that you have, you know, there's usually a bunch of small ones, and then there's a gap, and then there's a bunch of larger ones. And basically, these would be the numbers of clusters. So here, in this case, it would be 4 clusters, as you can see from the spectrum. So we know from the spectrum of, you know, putting in all these heat maps that there will be 4 clusters. And now we can inspect these clusters. And we can see, for example, that this is a cluster where we have heat maps that also contain this copyright tags, but they are portrait, right? This one is a cluster where they are landscape, also containing copyright tags. In computer vision, landscape and portrait are different statistics, in fact, in general. So then there's another class which is interesting, which is basically looking at hurdles. So it's recognizing horses because of context. And this is recognizing horses because of horses, right? So essentially, if you analyze what are the strategies implemented by a model, you can do this at scale. You can blazingly fast cluster really many, you know, millions of data points, billions, maybe more. And then, you know, instead of looking at every single heat map, you look at just a few representatives from each cluster, and then you find out what is the strategy. Okay. Now you can say, it's still, you know, why didn't you look at more recent, you know, data sets like ImageNet, and, you know, why didn't you look at VGG or any other modern architecture? Well, we did, right? And we wondered, do these architectures and these state-of-the-art models that everybody is very happy with, do they also have their clever Hans moment? And they do, interestingly. So here's one example which I like a lot. It's again a deep model. It's a state-of-the-art one, and it's classifying airplanes. So you just look at some representatives of this cluster here, and if you eyeball it, then what you see is the heat maps. They are basically looking like a little frame around the image. So, you know, it's classifying correctly airplanes, but the reason for it is some pixels at the edge. And so you wonder what's happening. Now, in computer vision, in order to get the pictures for our data sets, for our benchmarks, into the same shape and size, we do cropping, right? And the cropping puts some statistics on these pixels. It's done the same way since 20 years or so, and it's a cropping artifact that the state-of-the-art model relies on. So if you think about this cropping, the statistics of the cropping algorithm, then you realize that, yeah, maybe you can do it better and statistically more meaningful, meaning more random. And then if you actually do this and recrop these pictures and retrain, then you get better results, and suddenly these airplanes appear, in the middle of these heat maps. So practically, you can see that there's artifacts. You can see that there's methods that people have been using without further thinking much about it, and they actually, make these models get their clever Hans moment. Okay, so I think I should, just move forward very quickly because I've been taking way too much time. So, probably you know that in 2011 we had this very wonderful program where Anatole and Matthias Rupp and Alex came up with this nice PRL, basically suggesting that we use a machine learning model to predict the outcome of the Schrödinger equation. Okay, so that was the idea. And we had some very fascinating and great results. And nowadays, I think I have learned that Anatole was presenting something where it's below 0.3 kcal per mole, with more elaborate architectures than the kernel-ridge regression that we used back in the days, right? So, but you could say, well, nowadays we use deep learning like the SNET or the DTNN to solve this problem. And you could say, do these models also have their clever Hans moments, right? Because that would be devastating. So, nicely enough, they didn't, and we could, make some nice gummy bear plots, which are the equivalent of the heat maps, which reflect the chemical potentials. So we can do this for materials or also for molecules. But I would like to just show something, even beyond the supervised learning case that we have been talking about until now. So many of you may know anomaly detection. So you have a big data set, and then you map it into some feature space, and then you put a ball around it, for example, in support vector data description, which then corresponds to something nonlinear in the original space. That's the old kernel ideas in one-class classification. Now the question is, can we also explain that? And so the idea would be that we can rewrite, like a support vector machine as before, we can rewrite it in terms of a neural network, and then we can apply LRP. So that's the basic idea. And for example, if we look at some images or some examples. So here's an image, and let me take a very close look at it. Please, closer. Right? Can you see some anomaly in this? It's a famous psychology experiment. So it's basically the middle part of the picture is slightly tilted, right? So there's an anomaly. So the idea is that we take subpatches of this image, and these are the pictures. Then we do anomaly detection, and then we explain it. And then we can draw a heat map, and we can see that's the heat map here, right? So you can see that's basically the middle part that has changed. So this is now, again, some picture. What is the anomalous part? It's the lamps, right? The lights. So here you see a picture of a parking lot. So what's the anomalous part? Well, the car, right? And so on. So that's nice. So basically what you can do is you can take any old nonlinear one-class algorithm and use the same principles that I introduced and apply it. But we can also go further and say, could we also do this for clustering? So a lot of people apply some clustering algorithms, then they have their cluster results, and the question is, why is something a cluster? Okay? And so the idea here is that, you know, whereas in the case of, so if you take any kind of algorithm and you convert it to a neural network, so you can do this for one class, you can do this for clustering. So we call this neuralization because we transform it into a neural network. And then we can apply LRP. So how do you transform k-means into a neural network? So you have some data and some clusters, and basically you have a linear layer and a min pooling layer that does clustering. So that neural network can be analyzed with LRP. If you have kernel k-means, then you have some linear, some max pooling, min pooling, right? Or if you have deep k-means, then there's this conf something neural network architecture, and then you have, again, a linear and a min pooling part. Okay, so if we look at the results, for example, we could have some model that is a computer vision model. We look at, you know, in some parts of the representation, which is different layers, which have different abstractions, and we put the vector that is implemented in these layers, we put them into a clustering algorithm, and then we explain this. So you can see, for example, this is some layer 17. This is a VGG, I think, architecture. So in layer 17, we cluster all the activities from layer 17, and then so we could see that there's some particular background, edges, curvatures, something. But in layer 31, for example, we have clusters that are, for example, the dogs here, or the table clutter, or the lamp, or the painting. So some higher, concepts. Same here in this image. So you can just get an idea of what can be done. So just to wrap this part up, so all the explainable AI is not only limited to supervised architectures, but any kind of algorithm that is even unsupervised can be translated into a neural network architecture. This neural network architecture can then be analyzed in the way we typically analyze it. So we call this process neuralization. So it's very much so like back in the days when we kernelized any linear algorithm that was not fast enough on the tree, right? So let me stop here and come to a conclusion. So I was talking here about explaining and interpreting nonlinear models. Since we are using all these machine learning models nowadays in the sciences to gain some insights and have some predictions about quantum chemical properties and so on. So it is important to understand what they're doing and that they're not doing some artifactual nonsense. So, and some clever Hans, whatever. So therefore, I think it's a basic technique that we can apply to understand things. There's some theory going with it. It's a tool for gaining insight. So if you would like to use it, then there's a software, there's a website so this is collaboration with Wojtek Zamek's group at HHI. The main contributors are Wojtek Zamek, Grégoire Montavon, and Sebastian Lapushkin, and many others as well. So, for example, Malte Estas and Jakob Kaufmann for the unsupervised part. So you can get some tutorial. There's actually a new book that is actually out. So it's an old slide. And there's software that is quite popular these days. So you can just use it. And basically, it runs on the Keras. But there's also some PyTorch version being done. So this is now the explainable AI book that we have. It's a snapshot of the field. We ran several workshops at NIPS, and I think that was still NIPS then. NeurIPS, whatever, I mean so. And the book is an outcome of that. It's a snapshot of the field. In other words, we see stuff that has been made by the community. There are new developments there. For example, Gita in the afternoon will say something. So I think, you know, it's if you're interested to enter this, the website, the tutorial, and also the book may be good starting points. But if you just want to play, you know, the Keras toolbox is really helpful. Okay, so thank you very much.